And so we found a way to find the slope of the tangent line to a curve at a point, which is equal to the value of the derivative of a function at that x value. Now, we can generalize the whole process of finding this value by finding an actual derivative equation. We can do so by finding this limit here, which says that the derivative of f of x is going to equal the limit as h approaches 0 of f of x plus h minus f of x over h. Now, this derivative function will give us the slope of the function at any point where that derivative exists. Now, anywhere that derivative exists, we're going to say that that function is differentiable. And there'll be more on that in another video. Now, there are some common notations that you encounter when working with derivatives, and I have a list of them right here. We have dy over dx, which stands for the derivative of y with respect to x. Second one is f prime of x, which is the derivative of f with respect to x. And then another notation would be d over dx of f of x, which just means take the derivative with respect to x of f of x. We have f prime of 1, which is the value of the derivative of f as x is equal to 1. And then we have dy over dx with this documentation line here, and x equals 2. Basically, what this is saying is take the derivative of y with respect to x, and then after you do that, go put 2 in for all of your x's and see what the derivative is. And lastly, this notation here at the bottom, take the derivative with respect to x of f of x, and then put 2 into that derivative. Okay, so that's some notation. Now I just want to work on actually finding the derivative function or the derivative equation for f of x. We're going to use our definition of the derivative to do so. So that means that f prime, zoom in, so f prime of x is going to equal the limit as h approaches 0 of f of x plus h minus f of x over h. So this is going to give us an expression. So I already have f of x plus h is going to equal 2 times x plus h minus 1. And I can go ahead and expand that, and it'd be 2x plus 2h minus 1, and put that back into my limit. So the limit as h approaches 0 of 2x plus 2h minus 1 minus f of x. And I got to put the whole f function in parentheses so I get my signs correct. And then we simplify. And so the 2x's will cancel, the 1's will cancel, and I'm left with 2h over h. And we have the limit as h approaches 0 of 2, which is just going to give me 2. So the derivative function for this is just 2. So no matter what the x value is, we get 2. That should make sense because we have a linear equation which has constant rate of change. All right, then let's do it again here. So the derivative of x to the third minus x squared. So we're trying to find the limit to do this as h approaches 0 of f of x plus h minus f of x over h. So I need to find the f of x plus h so I can put it into that limit. And I need to expand those binomials. And so I got to expand the cube, expand the square, and rewrite. Okay, so that long expression is f of x plus h. Now we're going to put everything back into our limit. And so the x to the third and the x squareds cancel. Then I can reduce everything by h, kind of do two steps at once here. And then evaluate the limit, put in 0 for all my h's, and I'd have my derivative. So f prime of x would equal 3x squared minus 2x. So put in 0 for all the h's. Okay, now let's go the other direction. These are questions that you often encounter on a multiple choice exam where they're giving you a derivative in the form of a limit, and you have to interpret as to what that limit is actually telling you. So to prepare for that, I want to write the limit in the form as h approaches 0 to determine the instantaneous rate of change of f of x at x is equal to -5. Well, we can find the value of the derivative at -5 by evaluating the limit as h approaches 0 of f of -5 plus h minus f of -5 over h. So all I have to do is to do the function notation correctly. And all we're doing is writing. We don't have to simplify. So it'd be the limit as h approaches 0. Now it'd be e to the 3 times -5 plus h power minus e to the -15 power. So put -5 in for the x over h. And so there is my derivative or instantaneous rate of change in its limit form. Now let's do the same thing, but use the alternate way of writing the derivative, which instead of writing it as h approaches 0, we're going to write it as x approaches a number here, and it's going to be, I want to be find the derivative at x is equal to 5. And how do I know I'm doing that? Because the derivative is equal to the slope of the tangent line at that point. So this limit that we're trying to write would tell us f prime of 5 would equal the limit as x approaches 5 of f of x minus f of 5 over x minus 5. So I just put in 5 where I'm supposed to and do the function notation correctly. So that would equal the limit as x approaches 5 of my function of x, so the ln of x minus 3, minus f of 5, so it would be ln of 2, over x minus 5. Okay, so now we know how to find the equation, the derivative. Now let's make a big connection between the relationship between the graph of a function and its inverse. And so remember that the derivative equation is equal to the slope of a function at the point. And so when I'm trying to make a sketch of my derivative graph, I have to keep in mind that I need to actually plot what the slope is for the curve. So here in this first problem, and actually the first two we have, we're given the graph given the graph of a function f. We want to sketch the graph of its derivative on the same set of axes. So let me zoom in, and we just work one piece here at a time. So I start with this first function here. So I have the red piece, right? And I want to make a graph with derivative, and so the derivative is going to be dotted lines. And I'll try to color code it. So the value of the derivative, this is a line segment here, so the value of the derivative would be its slope. So rise over run. And it has a slope of -1. So from along those x values, those same x values, my derivative is always going to equal -1 until I get to that point. Now what I'm going to do is I'm going to put an open circle right there. Now let's look and see what the value of the derivative is for the next piece. So this next line segment, well, we'll go find the slope of that line, which is -3/2. So -1.5. So at -1.5, until I get, that's going to be the y value, until I get to x is equal to 1. And then once I get to x is equal to 1, the function is a horizontal line, which means that it has 0 slope, which means the value of the derivative is going to equal 0, so it's going to be going along the x-axis. Forgot I was doing dotted. And then we have our last piece, which is the right-hand side of the graph. And that has a slope of 2, so the value of the derivative along those points would be equal to 2. Now notice how I'm using open circles, because the graph, the f graph, the original one I was looking at, is not differentiable at those points due to having sharp turns and not being locally linear. So my derivative would have no value there, so I'm having open circles. All right, now we get to this next one here. So I want to sketch what the derivative would be. And that can be challenging. Now let's start with a point that we can identify the tangent line of. And for these, our relative extremas are good points to start with, because our relative extremas here would have horizontal tangents. If we were to zoom way in, I can't really do that because it's not on Decimus, but if I were to zoom way in there at that relative extrema, it would have a point, or it would look like a horizontal line. So my derivative there has to pass through the origin. Has to have a y value of 0. Now to figure the rest of it out. Well, the graph has positive slope. It's increasing, and then as it's working its way to its relative maximum, its rate of increase starts to kind of slow down. And so in terms of the value of the derivative, if I am increasing, that means my function, my derivative function, has to be positive there. And we're just sketching what that's going to look like. But you could try to estimate that by looking at some average rates of changes. I could try to pick 2 points and kind of look and say, that would have a slope of 6, or an average rate of change of 6 over that interval. And then the next interval would be 1, 2, 3, 4. Up 4 over 2, that would be 2. So that would be difficult for us to do. Now, we'll learn later how to do this, but what I'm going to do is, because I know I'm increasing, I know that the derivative has to be above the y-axis. And if I'm going down, it means I'm decreasing. That means my derivative function has to be below the x-axis. And so it's going to be decreasing this way. Okay, now let's start looking at trying to go the other way. So given the graph of f prime, so we're given the graph of the derivative, and we're told that f of 0 is equal to negative, or f of 0 is equal to 2. I want to try to attempt to sketch the graph of f in the same set of axes. Well, I know that f of 0 is 2, so I'm going to put that point on my graph. Now, I need to come up with a way to determine how to graph this. Well, I have a jump at axis 1, so something weird is going on at axis 1, but let's try to figure out, well, what is going on everywhere else? Let's start by doing this entire left side, because that would get me from the point that I know all the way off to the left side of the graph, and then to this point where something weird starts to happen. Well, this line has a y value of -1. That's representing the derivative. Because that's my derivative's constant, that means the slope of the line that passes through the points all along those x values are -1. So down 1, right 1. All right, so all the way to here. And then, let's see what happens when we get on the other side. Well, the entire right-hand side of 1 has a y value of 2. So at 2, or a y value of 2, so that's my derivative. So when I get to this point here, I go up 2 over 1, up 2 over 1. Now, why is it necessary to know f of 0 is 2? Because I needed a starting point to apply my slopes. All right, let's do another one. So next one, we're given the graph of the derivative of h. And we want to make some, we have a list, A, B, C, of items to determine. And for A, what is the value of h prime of 0? Well, we're given the derivative graph, so that's simple enough for me to say, oh, let's go get the y value there of 4. So h prime of 0 is equal to 4. What does that tell us about h? Well, because h prime of 0 is greater than 0, meaning it's positive, that means h is increasing. It's increasing at 0. So I know it has to be going upward to the right of 0, at least for a little while. Using the graph of h prime, how can we determine when the graph of h is going up or when it's going down? Well, I kind of already answered that. When the derivative is greater than 0, it's going to be increasing. Let's define that better. When the derivative is greater than 0, h is increasing, meaning it'll have positive slope. And when the derivative is less than 0, that means that the rate of change everywhere on h would be negative, so it would be decreasing. So for C, the graph of h prime crosses the x-axis at 2 and -2. Describe the behavior of the graph at these points. Well, that means that at x is equal to positive or -2, h has horizontal tangents. It also means that the graph is going from, the derivative graph is going from positive to negative, or negative to positive at those points, which in terms of increasing or decreasing means that we would have a relative maximum or minimum. And so think of it like this. So a relative max, we would go from increasing to decreasing. So there's the relative max. To the left side, my derivative would be positive because I would be going up. And the right side, because I'd be going down, my derivative would be negative. And vice versa. My minimum here, I would go from decreasing, meaning my derivative is less than 0, to increasing, meaning my derivative is greater than 0. Now, how can we tie all of this together on our graph that we have? And so what we have, because we're given the graph the derivative, is that in between 2 and -2, my derivative is greater than 0. So, or greater than 0. So that means I'm increasing in between. So from -2 to +2, h is increasing there. And h is decreasing when x is less than -2 and or greater than 2. So we try to think about, well, how can I make a graph that does that? So at 2 or -2 is when I have to change what it is I'm doing in terms of increasing or decreasing. And we don't have a point where the graph crosses through, so I'm just going to make a sketch that passes through the origin and try to meet all these characteristics. So it has to be increasing from -2 to +2, and then decreasing on the outside, so bigger than 2 or less than 2. So increasing till I get to 2. And then decreasing when I am less than 2, or excuse me, less than -2, or greater than +2. So decreasing and also decreasing. Okay, and you get better with that sketch, with the more information you have in terms of points you may pass through. This is just a generic sketch that meets the requirements that we have here.